Hello, sir. My name is Rand Franco. Thank you for joining us today. We are excited to share our insights on design and construction of sustainable road pavements for Road R43 in Hermanus, Western Cape. In this session, we will explore key findings, discuss essential methodologies, and the outline of results of our research. We appreciate your time and attention and look forward to an engaging presentation with you. The details of my team members can be found in the bottom left corner of the screen. They'll be introducing themselves when presenting their slides. For the presentation overview, we'll be looking at the objectives and the design guidelines for this project. For the objectives, the primary goal of this project is to evaluate and design a pavement system that effectively addresses the geotechnical and structural challenges associated with constructing a low-volume road in Hermanus, Western Cape. By assessing the stresses, strains, and the suitability of aggregates, the project ensures compliance with local and national guidelines such as Technical Guidelines 2, South African Pavement Engineering Manual, and the TRH4. This process involves integrating material testing, traffic analysis, and structural modeling to develop a cost-effective, sustainable, and durable road structure. For the design guidelines, our design adheres to the Technical Guidelines 2, which focuses on low-volume roads, providing practical approaches for the pavement design in resource-limited settings. The South African Pavement Engineering Manual ensures that the geotechnical, environmental, and traffic considerations are incorporated, while TRH4 offers additional insights into pavement performance under varying traffic loads.
Good afternoon, sir. I'm Aiden Dupree, and I will be discussing the project objectives. Number 1, evaluate soil and aggregate suitability. The foundation of any road is its subgrade and aggregate layers. To ensure these layers can handle the weight and movement of traffic, we need to understand properties like grading analysis, which is the size and distribution of soil particles, plasticity, how the soil behaves under wet conditions, density is how it's compacted, and the strength of the soil. To evaluate these properties, tests like the Californian bearing ratio and the dynamic cone penetration are used. These tests help us decide whether the existing materials are strong enough or needs improvement, such as stabilization using lime or cement. According to the South African Pavement Engineering Manual, Volume 4, these evaluations are critical for designing a stable road foundation. 2, determining stiffness using CBR values. Stiffness modeling are numbers that tells us how much the layer bends or compresses under a load. These values are calculated using CBR test results, which measures the resistance the soil is to pressure. The technical guideline stresses the pavement's layer stiffness, ensures it can distribute traffic loads evenly, preventing localizing damage. For example, a stiff base layer spreads the weight of vehicles over a large area, reducing the stress on lower layers. To ensure the pavement follows a mechanistic empirical design standards, which blend material properties in the real-world traffic behavior. Number 3, traffic loading estimation. Roads are designed to last for a specific time. In our case, our road is to last for 25 years. Over this period, the road will experience millions of vehicles that passes, even causing wear and tear. Using the TRH4 formulas, we calculate that these vehicles translate into a standardized measure called equivalent standard axle loads, also known as E80s. This makes it easier to predict the road stress levels and guide. The material selection is stronger materials are used in high stress areas. Layer thickness. The thicker the layer are needed to handle higher loads. Number 4. Design pavement for durability and cost effectiveness. A durable pavement must balance strength, cost, and longevity. Using high quality materials may cost more upfront but reduces long-term maintenance costs. Designing layers with varying strengths ensures each layer does its job without overloading another. Following the technical guidelines cost-benefit analysis, we ensure that the designs perform efficiently throughout its life, reducing frequent repair and disruptions. The site characteristics or other location and environmental factors. For your site characteristics, the road is located near the coast in Hermanus, which poses unique challenges such as the coastal conditions, where it has a high humidity and exposure to salt can accelerate material degradation. The Mediterranean climate. Winters bring heavy rains while summers are dry. The constant change in impact on subgrade moisture levels, leading to swelling and shrinking of soil. To address these issues, the South African Pavement Engineering Manual, Chapter 6 suggests a thorough geotechnical investigation and using materials resistant to environmental stress. Environmental impact. Coastal areas often face salt erosion and moisture penetration, which weakens road materials. The technical guidelines recommend countering these effects by adding proper drainage systems to remove water quickly, using materials with low permeability to block water infiltration, and applying a weather-resistant materials as the TRH4 advises to extend the road's lifespan. Climate influence. Rainfall during winter causes waterlogging, which reduces the soil strength and load-bearing capacity. Without drainage, water can seep into the pavement, causing cracking and potholes. To overcome this, the South African Pavement Engineering Manual, Volume 4, recommends installing surface and subsurface drainage systems linked to a lined ditches, cross slopes, and perforated pipes. Materials must also be carefully graded to allow water to flow, protecting the subgrade from moisture damage. Geotechnical conditions follows under soil types, drainage needs, and subgrade strengths. The soil types. Coastal soils are mostly sandy. They drain water well, but are weak in supporting load-bearing capacity. Inland soils are mostly clayey. They expand and shrink with moisture changes, causing cracking. The South African Pavement Engineering Manual, Volume 3, recommends stabilization techniques to control the behavior and maintain a stable pace. Drainage needs. Water infiltration is one of the biggest threats to the pavement. Poor drainage can cause erosion, where soil particles are washed away and weakening the foundation. Strength loss. Wet soils lose their ability to support loads. The South African Pavement Engineering Manual, Chapter 7, outlines drainage solutions, where perforated pipes and geotextiles are to manage underground water, whereas the lined ditches handles the surface water flow efficiently. Subgrade strength. Subgrade strength. The subgrade layer acts as a foundation for the entire road. If it is too weak, the upper layers will fail. CBR test measures how much pressure the subgrade can handle. The TRH4 specifies acceptable threshold, and anything that below this requires stabilization with additives like lime and cement, and replacement with stronger materials if the stabilization is not feasible.
We will discuss the laboratory testings conducted. We will look into the CBR testing, grading analysis, and the DCP test. As outlined in the TG2, the CBR test is a widely used method for evaluating the strength of subgrade soil and its ability to support the stresses imposed by traffic loads. This test involves applying a standard load to a soil sample and measuring its penetration. The CBR value is then calculated by comparing the soil's resistance to that of a standard material, usually crushed rock. Higher CBR values indicate stronger subgrade materials capable of supporting heavier loads without excessive deformation. The results for CBR testings are crucial in designing the pavement structure, particularly for determining the thickness of the base and subbase layers. A higher CBR value allows for thinner pavement layers, reducing both material and construction costs while maintaining structural integrity. Grading analysis following the South African Pavement Engineering Manual, Chapter 6 guidelines, involves determining the particle size distribution of the soil or aggregate material. This test helps to assess the proportions of different size particles within the material, which directly impacts the material's load distribution and drainage properties. Well-graded materials, which have a balanced range of particle size, tend to interlock more effectively, offering greater strength and stability. Additionally, a good grading ensures adequate permeability, which is essential for preventing water buildup beneath the pavement that could weaken the foundation. The grading analysis helps determine if the material is suitable to be used in the base or subbase layers if necessary. For the DCP testing, as referred to in the TRH4, it is an in situ method for assessing the strength and resistance of subgrade soils and pavement layers. The test involves driving a cone into a soil using a hammer, and the number of blows required to penetrate a certain depth is recorded. The DCP provides real-time information about the strength of the material at various depths, allowing for a more comprehensive understanding of the subgrade's variability across the site. Areas with low resistance may indicate weaknesses or the need for additional stabilization. DCP testing is essentially useful for identifying specific zones that may require interventions, such as soil stabilization or reinforcement, to ensure a uniformly strong foundation for the pavement.
Good day, sir. My name is Kitumetse Nonyana, and I'll be presenting on traffic analysis and road pavement design. So, traffic analysis. The main goal of traffic analysis in this project is to estimate the traffic loading over the road design's life of 25 years and its impact on pavement performance. So, this ensures that the road can accommodate the stresses posed upon it over the design life period. So this begins with first collecting data from the Road Network Information System, the RNIS. And for this road, it was determined that 22,223 vehicles were passing over the road segment on average per day over a year. This information told us also that 5% of heavy vehicles were passing over the road, which led to a value of 1,101 vehicles. Using the formula, it was also determined that we can calculate the equivalent standard axle loads, referred to as EATs. It was determined that 25.3 million axle loads were acting on this road segment, that would relatively place that the road is a category A road. And for the layer design requirements, the base and subbase layers must be designed to handle the cumulative load efficiencies, and the surfacing layer should resist fatigue and rutting and cracking, resulting in a material selection of high quality materials with appropriate stiffness and load bearing capacity. This places the road under category A, which according to the South African Pavement Engineering Manual, and it supports between 10 to 30 E80s over its design life. So what do these calculations mean in terms of pavement design? The traffic analysis has several implications on pavement design. It classifies the road as a category A road due to its high traffic load, necessitating a robust design of pavement solutions. For the layer design requirements, the base and subbase layers must be designed to handle cumulative load efficiency, and the surfacing layer should resist fatigue, rutting, and cracking, resulting in a material selection of high quality materials with the appropriate stiffness for load bearing capacity, which are essential to durability. The results and recommendations for traffic analysis are as follows. Okay. For the traffic volume impact, the road is expected to sustain approximately 25.3 million E80s over a 25-year design period, right? What does this mean for structural durability? The pavement design must include materials and layers that prevent premature failure under heavy traffic. And for a maintenance plan, periodic resurfacing and maintaining, especially of the asphalt layer, are necessary to manage wear and tear of traffic loads. In conclusion, the traffic analysis establishes the foundation for designing a road that can handle heavy loads while being cost-effective and durable. It emphasizes the importance of understanding vehicle types, traffic volumes, load equivalencies to create a resilient pavement structure tailored to the demands of the Hermanus area. And now on to road pavement design. The purpose of road pavement layer design. The pavement layer design is a critical aspect of road construction that ensures that roads can support traffic loads, withstand environmental conditions, and remain durable over its intended lifespan. The main objectives of designing pavement layers is to distribute stresses along the road caused by traffic loads, to prevent failures, provide a safe, durable, cost-effective surface for vehicles, thereby ensuring longevity, reducing maintenance costs over the 25-year design period. The design in this project adheres to the South African Pavement Engineering Manual and the technical guidelines of the TG2 standards. The structure of pavement layers. A well-designed pavement typically consists of multiple layers, each serving specific functions. Right? The proposed design for our road includes the following layer: the surfacing layer. The surfacing layer, which is comprised of asphalt concrete with a thickness of 50 millimeters, its purpose of which is to protect the underlying layers from environmental damage, such as moisture, temperature fluctuations, and provides a smooth skid-resistant surface for vehicles. Materials used should be bituminous asphalt, concrete with a high resistance to rutting and fatigue, ensuring longevity under stresses. For the base layer, the purpose of providing structural support and helping distribute traffic loads to the lower roads, a thickness of 150 to 200 millimeters with materials of high-grade quality G1 or G2 crushed stone with a stiffness modulus suitable for high traffic loads. For the subbase layer, with the purpose of acting as a transition layer between the base and the subbase grade, spreading loads and providing additional support, a thickness of 150 to 200 is also suggested with materials of G4 to G5 graded materials, of crushed stone and natural gravel with adequate compaction. And now onto the selected subgrade layers which are fundamental in the pavement structure as they form the transition between the natural subgrade and the subbase layers. Their purpose is to enhance the load-bearing capacity, distribute stresses, and provide stability to the upper layers. In this project, the selected subgrade is divided into two parts, the upper selected and the lower selected subgrade layers. The material here is a G7 subgrade for the upper selected subgrade layer, and it consists of coarse-grained soil. It has a CBR requirement of 20 to 25% to provide sufficient stiffness and prevent excessive deformation under traffic loads, the thickness being 300 millimeters. This is the layer directly beneath the subbase. For the lower selected subgrade layer, the material consists of a G8 material, slightly lower quality than the G7. The CBR requirement is 15% or greater, ensuring adequate support of the pavement structure with the same thickness of 300 millimeters. This layer is directly below the subgrade layer and above the natural subgrade. In conclusion, the pavement layer incorporates advanced engineering principles and practices to ensure a robust, durable, and cost-effective road. By focusing on traffic loads, material quality, drainage, and proper construction practices, the design meets both functional and safety requirements of the Hermanus road segment. This meticulous approach guarantees the long-term performance of the road over the design period.
Okay. Good day, sir. My name is Naam Surakaibe, and today I will be covering the key findings, the recommendations, and the conclusion of this presentation. Starting with the subgrade evaluation. The subgrade is a fundamental component in the design of any road pavement as it supports the weight of the traffic and the structure above it. In the case of the road that's in Hermanus, which is the R43, the subgrade testing was carried out using the methods of the CBR and the DCP testing. The findings from these tests are as follows, or the conclusions that we've made. The subgrade soils in this region vary from sandy soils near the coast to clayey soils further inland. Sandy soils tend to have a good permeability but low bearing capacity, meaning they can become unstable under heavy loads. These areas might need reinforcement using lime or cement to enhance their load-bearing capacity. They also have clayey soils, which are expansive and can shrink or expand depending on the moisture content. The test results, which is the CBR and the DCP tests that we've conducted, the CBR values were found to be highly variable. Layer 1, which is closer to the surface, exhibited a high CBR value of 53%, indicating that it provides a strong foundation for the pavement. However, the deeper layers, specifically layer 2 through layer 6, showed a much lower CBR value, ranging from 23% to 29%. These values suggest that these layers are not strong enough to support heavy traffic loads without any type of treatment or stabilization. The DCP results also revealed that the penetration resistance of deeper layers was lower, especially in the sandy and clayey soils, which indicates that these layers are prone to deformation under loads. This finding supports the need for the stabilization or any type of reinforcement in these weaker subgrade layers to prevent excessive settlement or failure. We then go into the drainage requirements. Drainage plays a critical role in road pavement, especially in areas that are prone to moisture levels like coastal regions. Proper drainage prevents water from infiltrating the subgrade and pavement structure, which could reduce the subgrade strength and lead to a premature pavement failure. We look into the subbase drainage to prevent water accumulation on the pavement surface, which can lead to issues like potholes, crackings, and erosions. We want to facilitate water runoff. The pavement design incorporates cross slopes and a camber of 2.5 to 3%. These slopes direct water away from the pavement surface into adjacent drainage systems, ensuring that water does not accumulate or cause surface degradation. The subsurface drainage. This regions that we have, which is in Hermanus, specific to coastal roads, is prone to high moisture content, which can affect the strength and of the subgrade layers. To address this, We suggest the installation of fabricated pipes and geotextiles beneath the pavement structure. These materials allow for effective drainage by preventing water from accumulating in the subgrade and ensuring that groundwater does not infiltrate into the pavement layers. The use of these geotextiles helps in reinforcing the subgrade layer and material and preventing the migration of the fine particles which could compromise the stability of the base or sub-base layers. Additionally, these pipes will allow excess water to be redirected away from the pavement structure, maintaining the strength and integrity of the road over the 25-year period of design. Our area is also in a coastal region, and coastal areas face additional challenges such as saline water and erosion due to the wave action and wind. The drainage system should be designed with these factors in mind, using corrosion-resistant materials for the pipes and ensuring that the drainage components can handle the corrosive effects of salt water. Special attention should be given to the geotechnical properties of the soil, as the interactions between the soil and the water, particularly in saline water, can affect the stability of the pavement. Proper drainage will help mitigate the impact of the moisture-related issues such as erosion, waterlogging, and loss of the subgrade strength. We then move on to the MEPAD analysis. The MEPAD analysis provides a comprehensive understanding of the structural performance of the proposed pavement design under expected traffic loads. MEPAD is a tool that we use to model the stresses, strain, and deflections within a pavement structure, allowing for accurate predictions for the pavement behavior over its design life. The stress and strain distribution. The MEPAD analysis showed the distribution of both compressive and tensile stresses across different pavement layers, indicating how the material reacts under applied loads. The deepest layers, such as the EG5 and the EG6 cemented layers, experienced a high compressive stresses, which is expected as they support majority of the load. These layers are essential for maintaining pavement stability and preventing excessive deformation. The asphalt surface layer, which is more prone to tensile stresses, was found to experience tensile strains that could lead to cracking over time. The analysis revealed that the tensile strain in the asphalt layer is below the critical threshold of 140 microstrain, ensuring that the asphalt layer can withstand expected traffic loads without significant fatigue failure. This is critical for maintaining the surface layer's integrity throughout the design year of the 25 years. The pavement layer performance, the cemented layers, the EG5 and EG6, exhibited extremely high safety factors and bearing capacities, indicating that they are highly resistant to failure and will provide a long-term support for the pavement structure. These layers contribute to the overall strength and stability of the pavement and ensure that it can withstand repeated traffic loads. The granular layers, which is G2 and G5, these layers were moderately stressed. They require careful compaction to ensure optimal performance. The MEPAD analysis suggests that the granular layers should be well compacted to achieve the necessary stiffness and prevent excessive deformation over time. The granular materials such as G2 and G5 are important for distributing the traffic loads to the subgrade, and their performance is critical in preventing the differential settlement. The factor safety and the durability of the analysis. The analysis confirmed that all pavement layers exhibit safety factors greater than 1, indicating that the pavement structure is designed to resist applied loads without failure. The factor of safety for each layer ensures that the pavement will perform well under expected traffic conditions and will not experience permanent failure. The fatigue and deformation resistance. The MEPAD analysis also assessed the pavement's resistance to fatigue and deformation over the 25-year period. The analysis indicated that the asphalt layer is durable and capable of handling expected traffic volumes, which is the E80s, without exceeding critical strain thresholds. However, periodic monitoring and maintenance will be required to ensure the surface layer does not degrade prematurely, especially under heavy traffic or adverse weather conditions. The takeaway from the MEPAD analysis was that the pavement structure, with its combination of the cemented and granular layers, provides a significant strength to withhold 35.6 million E80s over the design period of 25 years. The analysis confirms that the pavement design is resilient under expected traffic loads and climatic conditions. Although the asphalt layer is durable, it will require periodic maintenance due to its susceptibility to fatigue under repeated loads. The cemented layers ensure the pavement's long-term stability and reduce the risk of failure, supporting both the traffic load and environmental factors. Based on the findings of the subgrade evaluation, the drainage design, and the MEPAD analysis, and overall the project that we've conducted for our geotechnical evaluation for the roads, we can conclude or recommend the following recommendations to enhance the durability, performance, and cost effectiveness of the pavement design. Subgrade stabilization. Stabilize the weaker subgrade layers, layer 2 through 6, using lime, cement, or geotextile reinforcement to improve their load-bearing capacity. The subgrade in these layers exhibit a low CBR value, indicating inadequate strength for supporting traffic loads. Stabilizing these layers will prevent differential settlement, improve the structural integrity of the pavement, and ensure that uniform load distribution across the road structure. The second recommendation would be in terms of drainage system enhancements. Surface drainage, the implementation of the camber and cross slope of 2.5 to 3% to facilitate the water runoff from the pavement surface, directing it towards the drainage system, such as line ditches and riprap in areas where the flow is concentrated. The subsurface drainage, the installation of perforated pipes and geotextiles underneath the pavement to manage the groundwater and prevent water infiltration into the subgrade. This will ensure the subgrade remains stable under varying moisture conditions, especially in coastal regions with high rainfall areas. The effective drainage is essential to reduce moisture-related damage, such as erosion and reduced subgrade strength. Proper drainage management will extend the lifespan of the pavement by preventing the accumulation of water within the designated layers. The third recommendation would be the usage of well-graded aggregates for the base and sub-base layers, such as the G1 and the G2, with crushed stone for the base and G4, G5 materials for the sub-base. The asphalt layers should consist of high-quality asphalt, concrete, AC, with a suitable binder, such as the SBS or the AP1, to resist rutting or fatigue. Well-graded aggregates enhance load distribution and reduce voids, improving the stiffness and stability of the pavement. Asphalt mix optimization will ensure durability, resistance to deformation, and adequate flexibility under varying temperature and traffic conditions. The fourth recommendation has to do with the pavement layer maintenance. To conduct a routine maintenance, particularly for the asphalt layer, to address early signs of wear or fatigue. Resurfacing may be necessary after the first 10 to 15 years to maintain the road pavement's structural integrity. The asphalt, being more susceptible to fatigue and repeated loading, should be monitored regularly for cracks, ruts, or surface distress. Maintenance will help extend the road's surface life and reduce the need for major repairs. In conclusion, the geotechnical and pavement design analysis for the R43 road in Hermanus Road project provides a comprehensive assessment of the pavement's structure, suitability to withstand the expected traffic loads and environmental conditions over the next 25 years. The study incorporated a range of tests, which is inclusive of the subgrade evaluation, the grading analysis, the MEPAD analysis and simulations, leading to the following conclusions. With the subgrade performance, the subgrade layer exhibits significant variation in strength, while the upper layers, which is layer 1, provide adequate support with the CBR value of 53%. Deeper layers, 2 to 6, have a lower CBR that indicates stabilization methods such as lime, cement treatment, or any other relevant stabilization method. Drainage design. With the drainage design, the analysis highlighted the importance of both the subsurface and the surface drainage solutions. With the region's coastal climate and seasonal change of rainfall, the implementation of proper camphor, the cross slopes, perforated pipes, and geotextiles is critical in preventing water infiltration into the pavement structure, thereby ensuring long-term stability and preventing moisture-related degradation. The MEPAD analysis demonstrated that the proposed pavement structure, comprising of asphalt, granular, and cemented layers, is capable of supporting 35.6 million EATs over the design period of 25 years. However, the asphalt layer is susceptible to fatigue and it requires periodic maintenance. The cemented layers, in particular, provide excellent load-bearing capacity and long-term resilience. Furthermore, based on the grading analysis, the selected materials meet the necessary specifications for the construction of the subbase, base, and asphalt layer. Proper selection of these materials, including the G2 and G5 graded aggregates, ensures that the pavement structure is durable and cost-effective while minimizing maintenance needs. The overall design variability of this road is classified as a category A. It is suitable for the projected traffic loads and environmental conditions. The design is cost-effective and durable, meeting the requirements of the South African Pavement Engineering Manual and the technical guidelines too. The road is expected to perform reliably over the next 25 years, with minimum maintenance required, aside from the periodic resurfacing of the asphalt layer. In conclusion, the proposed pavement structure with proper stabilization, drainage, and periodic maintenance will provide a resilient and long-lasting solution to the Hermanus Road, which is the R43, supporting both the functional and the social needs of this region.